Okay, welcome to the third note set in the first unit of the digital audio signal processing class. Here we'll talk about group and phase delay of filters. We're going to focus on discrete time, but everything we say can be carried over to continuous time with just the obvious modifications. And the resource that I'm basing these notes on is a book by Boaz Parat called A Course in Digital Signal Processing. And here's the sections that I'm drawing this material from. Great book, probably my favorite book on digital signal processing. A little more mathematical than many of the other books, but if you really want to learn the theory of DSP, that's a great resource. So everything in this set of notes and pretty much everywhere else in this course, we will focus on a certain class of filters with some mathematical constraints. And we call those real, causal, stable, and rational filters. And so let's start with the rational part. That means that the transfer function is a rational function of z. And that just means it's a ratio of two polynomials in z, although here we're showing it equivalently as a ratio of two polynomials in z inverse. So just think about z inverse raised to the first power, z inverse raised to the nth power for the two components that I have circled there. And you can see the notation I use here, H. Capital H is our notation for transfer function. Sometimes I'll put a superscript or a subscript on these to draw attention, and when I do, I'll point that out. So rational, ratio, is right there in the name. Okay, the second thing, the real part means that the coefficients are real valued. So all the A's and B's here are real valued numbers. Also, I should point out, notice that I've normalized the first coefficient in the A polynomial in the denominator. That's common. We can always do that. If it's not normalized to 1, you just take that number and divide top and bottom, the top polynomial and the bottom polynomial by that number. You haven't changed anything because you're dividing top and bottom by the same number. And that will normalize it this way. So we don't lose any generality by doing that. By making these coefficients real valued, it imposes certain constraints on the poles and zeros. So remember, the poles are the roots of the denominator and the zeros are the roots of the numerator after we've converted into Z form. So I cover that in the review video and notes. So you might want to go back and look there. The poles and zeros have to appear in complex conjugate pairs. So you could have real valued poles and zeros that are just singletons. But if they are complex, there will always be, in addition to that pole or zero, its complex conjugate on the Z plane will also exist. The C is the causal part. We'll refer to these as RCSR, I guess, or some other combination of those initials. So the causal part has to do with the impulse response, or at least that's the easiest way to characterize the causality of it. So there's a more general definition of causality, and you should have learned that in your signals and systems class, and I'm not going to go back and address that at this point. But from our point of view, once we have the transfer function, we take the inverse Z transform, and the thing that we get is the impulse response. So remember, that is the thing that comes out of the system if we put in a discrete time delta function. Remember, discrete time delta function goes to 1, not infinity like a continuous time one. And it's 0 everywhere else. So here's the idea. If the first non-zero thing that hits the system is at time n equal to 0, then there is no way that the system can anticipate that that's going to happen. And so the first non-zero value of the impulse response must occur at n equal to 0 or later. So that's why we say here that h of n must be equal to 0 for all n less than 0. So that's causality. And that also imposes some constraints on the kinds of filters that we can talk about. And then the final thing is stability. So you can see what I've done here is I've taken this and I've effectively multiplied top and bottom by some power of z to clear out the negative powers. So this is the polynomial in z associated with the denominator. So that's the polynomial that's set to where the poles are. Again, if these concepts are not clear to you, you should go back and look at my review video for this course. So the poles must be inside, strictly inside the unit circle, not on the edge of the unit circle, strictly inside. So magnitudes strictly less than 1. So UC stands for the unit circle. So that makes the system stable. That also ensures that the impulse response decays in some way fast enough to make the system a stable system. So we'll call these RCSR filters for short. I'm not sure I ever used that abbreviation later, but that's what Peratt calls them. And so every statement in this set of notes and virtually every other set of notes in this course will be made for this type of filter without stating that. And if there's any other, if there's any, scenario where we're not considering RCSR filters, we'll make that clear in the statements in later notes. Everything in this note set is for these. Okay, so we've got the transfer function, and there's a couple different ways of expressing the frequency response. If you go back and look at my review notes for this course, you'll see that I use some other notation, but this is a common way. We're just taking that h of z and replacing it by e to the j omega so that we get a function of omega, but really it's just looking at the transfer function evaluated on the unit circle. As we let omega go from minus pi to pi, we're walking around the unit circle like this. So that's what we're really doing here. So this is the real part of z, and this is the imaginary part of z. And we're looking at that h of z function on the unit circle. So in this note set, I will exclusively use this notation with this argument inside. Other places, I'll define a new function, h of omega, that's the same as this one. Or I'll usually have some subscript or superscript to draw a distinction between that and the h for the transfer function. Okay, so it's complex valued. So remember that real thing in the RCSR characterization was that the coefficients are real, but the function itself is complex valued. So we can write it in polar form. So polar form means put its magnitude out front and then its angle up in an e to the j thing. And by its very definition, polar form must have, since we're talking about the magnitude that's like absolute value, that cannot be negative. So we'll write this thing as m of omega, at least in this note set, and m of omega cannot be negative. And then this thing here will just denote as psi of omega. And I say that it lies between minus pi and pi. Well, remember, angles in a polar form are ambiguous by multiples of additions of multiples of 2 pi, right? If I'm sitting here at this angle, I can say it's this angle, so like pi over 4-ish, but I could also add 2 pi to it, and I'm right back to where I was. So angles are 2 pi periodic in some sense, or 2 pi ambiguous. But we often enforce that mathematically we say, we'll say that they lie between minus pi and pi. And that becomes somewhat of a problem. And that's one of the things that we'll address in this set of notes is how to deal with that. Because something weird happens as we go from minus pi. Remember, minus pi and pi are exactly the same angle, right? They're exactly the same position. So if we are at minus pi and we go just a little bit more negative, suddenly we're going to jump from right here to something that's over on that side of that interval. And that creates a discontinuity, and that's one of the things that we'll talk about here. We're just talking about the phase of the frequency response here. So this constraint, as I said, comes from the fact that the magnitude of something is never negative. And this constraint just comes from the fact that we can always insist, or as a convention, we can choose the angle to lie between minus pi and pi. And sometimes that's convenient, and sometimes it's not convenient. But regardless of whatever we say the angle is, remember, there is infinitely many other angles that could be used equally well in the mathematical definition of the frequency response at that point. So that's the weird part. And these constraints carry over into MATLAB's commands. So MATLAB has an ABS command. So if you computed the values of this frequency response and put them into some vector h, you could find the m values, the magnitudes, by just doing ABS of h. And likewise, you could find the angles here by using the angle command. So this thing here is going to be strictly greater than or equal to 0. And when MATLAB computes the angle of h, it will put it between minus pi and pi. It may exclude one or the other ends of those. I can't really remember. But that's a subtle distinction. So each of these constraints cause some discontinuities in the phase. Obviously, we've seen and alluded to this one. That one's pretty obvious. What's less obvious is that this constraint also leads to a discontinuity, and we'll state that. I won't prove it. Comes out of the theory of complex valued functions from mathematics. Or at least a class of complex valued functions. But it comes from those RCSR constraints. If you have such a transfer function, then you'll get this discontinuity from these constraints. So let's take a look at these. There are two different types. So type 1 just comes from the fact that the angle mathematically and inside MATLAB is constrained to lie between minus pi and pi. And again, I'm showing closed intervals here. If you want to get fussy, technically one of those could be left open, and I'm not sure which one MATLAB does, if it even bothers with that. But again, subtle issue. So let's look at an example. Here's a transfer function. This is a simple form, 1 plus 2 z to the minus 2. And I'm showing plots of what MATLAB would give you for the magnitude of that and for the phase. So this would be computed. Using the ABS form, and this would be computed using the angle form. After you put this into freq z over the range from minus pi to pi. So remember, I like to normalize my discrete time frequencies by pi, so I get these nice mile markers. Otherwise, MATLAB doesn't put nice mile markers at like pies and half pies and quarter pies and things like that. And then this is computed using the angle command, and you can see that it has limited it between minus pi to pi. And you also see that, this looks like it's getting more and more negative, and then it gets down to minus pi. And technically, this could continue on. So imagine this thing moved down here. That is mathematically valid, but it violates that condition. And MATLAB says, I can't represent an angle down here, so it represents it up here. So there's that discontinuity. I show it in the plot with a vertical line there, but there's really no vertical line. right? It just comes down to here and then discontinuously jumps up. Okay, MATLAB just draws lines between successive points, so that's why it looks like that. Okay, so this can be fixed. Sometimes we want to see it without that discontinuity. Just helps us visualize it. So MATLAB has a command called unwrap that will fix these type 1 discontinuities that occur just because the phase appears to want to go outside of that minus pi to pi, and the angle command just wraps it back inside pi. That's a good way to think about it, right? It looks like it should go a little bit farther, and it just wraps it back over to here. So that's the idea. So I can get this unwrapped phase by doing this command for this case. Now, here's the angle command, and then notice that I've wrapped and unwrapped around that. Two uses of the word wrap there. And then I've added 2 pi. We'll talk about that in a minute. So all the unwrap command does is it does the following thing. I had to scoot ahead there just a little bit to see where I was going. All the unwrap command does is it starts at the left side of the vector. So this angle H is going to give us this thing here. So once the angle computes this thing, you've got this thing in a vector in that order. So it starts at the beginning of the vector and it says, oh, I'm looking for jumps of 2 pi, right? This is a 2 pi jump as it crosses that plus or minus pi boundary. So it's going along, okay, nothing. It gets down here and then it senses that jump. And there's a little tolerance in there because it might not be a perfect 2 pi jump because of the spacing used to compute this thing might be a little too coarse to see that perfect 2 pi jump. But there's a tolerance in there. So it's looking for something that is about a 2 pi jump. And when it sees that, it says, oh, I should take the next set of values and really I should move them down. I should make this point, this section align with this section. So everything gets moved down. So I'm going to try to draw this. So this whole section gets moved down. In fact, all of this gets moved down, and then this jumps up like that. So that's what happens inside the unwrap command. And then it continues, and it sees another 2 pi jump. So that's this 2 pi jump that's been moved down by 2 pi. That's not this thing. That's happening inside the unwrap command. And so the unwrap command senses that and now moves this down here further. So now what do we have? We have something that starts at 0 and goes all the way down here. That's not really convenient. We would like to have retained that odd symmetry of phase. Now we can, once we've run the unwrap command, we can add or subtract any integer multiple of 2 pi to the whole damn thing. And so that's what we do. We notice that this point ends up here 2 pi down. So it's at minus 2 pi. So minus pi there, minus 2 pi down. And so we need to move that up to 0. And so that's what we do here. So you have to play with that. You have to kind of see. There's no easy way to figure that out. So that's why I'm adding the 2 pi here. Now, if it turned out that, that center point at omega equal to 0 turned out to be up 2 pi or down 4 pi, I would adjust what I add here. But it would always be some integer multiple of 2 pi. So that's what I say there. An optional thing, you don't always have to do this, but it's nice, is you add multiples of 2 pi. So add, so those multiples could be negative multiples, right? Could be like minus 3 times 2 pi. So you add multiples of 2 pi to center this thing this way, vertically, to center it so that at omega equal to 0, it's centered at omega equal to 0. and I guess centered is perhaps maybe incorrect. The right, what I mean by centered is at omega 0, it goes through 0. That's the idea. Then we have this nice odd symmetry. Another option, though, is in many of our audio applications, we don't do the negative frequency side because we know what's going to be out there. There's this symmetry, right? So we often just look from 0 onward in the positive direction. So let's see what would happen if we do this. So if we were to not compute this. So when we did freq Z to get this H, we're not doing the negative frequencies. We're just starting from the positive frequencies. Note that that starts at 0. So the unwrap will leave it at 0 because it doesn't make a change until here. Now it's going to bump that down. And so this plot would start right here. And we would not need that 2 pi because unwrap didn't have to adjust that point, because it never sees that discontinuity. So either way, retains this odd symmetry. One way shows it explicitly, and the other way, we know that if we've done this the way we should do it, and are just showing the positive frequencies, the negative frequencies will have that odd symmetry. Okay, so that's the type 1 phase discontinuity. So it's not important the name type 1. What's important is that type of phase discontinuity comes from the phase, the computed phase, being constrained to minus pi to pi and jumping across that minus pi plus pi boundary. Okay. Type 2 comes from the constraint that the magnitude must be non-negative. And again, I'm not going to prove this, and it's not as obvious as the previous one. But if you start with an RCSR transfer function, one can prove using theories from mathematics, complex functions, something called analytic function theory. You can prove that for these kinds of frequency responses, whenever m of omega goes to 0 at some particular omega value, you will get a pi jump in the phase. So that'll be a pi jump discontinuity. And so here is an example. I've chosen one that goes to 0. So it goes to 0 at 0. Doesn't have to go to 0 at 0. The place it goes to 0 could be at some other frequency, but that's where it is for this particular example. So this is computed using the ABS. After we've put this into freq Z and computed from minus pi to pi, we apply the ABS command and we'll get this function or that plot. And then we apply the angle command and we'll get this. And now you can see, well, there's no type 1 discontinuity because everything lies between minus pi over 2 and pi over 2. So everything is good. Nothing getting even close to that minus pi plus pi boundary. But we see a jump here. And again, there's really no vertical line there. It's a discontinuous jump, just like you learned about in your calculus classes. And it's going, in this case, from minus pi over 2 to pi over 2. Doesn't have to be from minus pi over 2 to pi over 2. All that matters is it's a pi jump. In this example, it just happens to go from minus pi over 2 to pi over 2. Could go from, minus pi over 4 to, would it be 3 pi over 4, something like that. Any pi jump is okay, is valid for this scenario. Okay, so note here that in this case, the magnitude has the even symmetry and the phase has the odd symmetry, just like we learned in a signals and systems class, that when we write things out in polar form, and when we write the frequency response out in polar form, the magnitude will have even symmetry and the phase will have odd symmetry. Now, also remember that whenever something goes to 0, when the magnitude goes to 0, the angle really is undefined, right? if we're looking at a complex plane, so here's the real axis and the imaginary axis. I'm not looking at the z-plane. I'm just looking at a general complex plane, and I look at a complex number with some magnitude and some angle. So there's the magnitude and there's the angle. That makes sense. But what if I say, let's see if I can erase this. What if I say, here's my point. It's 0 at what angle? Where does it point? The concept of a 0, a single point, pointing in a direction makes no sense. It's undefined. So another way to think about it is it could be anything that we want. So it doesn't really matter what it is. So the angle at 0 is arbitrary, undefined, however you want to think about it. And this is the part that I said one can show through that more complicated mathematics of complex functions. Whenever this thing goes to 0, so there's some particular frequency at which this thing goes to 0. I'm not saying that it's identically equal to 0 for all frequencies, just like this, okay? The phase must change by plus or minus pi. Now, that is something that cannot be fixed by MATLAB's unwrap command. So we need to work a little bit harder. And sometimes we don't actually explicitly do this in our plots. We might just need to think about it. But sometimes we do want to explicitly show it, and we'll have to work a little bit harder. And so this leads us to something called the continuous phase representation. So this idea is necessary to handle these pi jump discontinuities. So if you have a transfer function whose frequency response never hits 0, never hits magnitude equal to 0, you don't have to worry about this continuous phase representation. But it is a more general way of thinking about frequency responses. So sometimes we just automatically go there. But most of the time we just kind of, if we need to, we do this. And like I said, we may do it explicitly, or we might just think it and do it implicitly. But let's think about how we do it explicitly. So what we need to do is abandon the magnitude and phase. So remember, the magnitude part here was, because it's a magnitude, it's an absolute value in a sense, must be non-negative. And so what we're going to do is replace that with an amplitude view, which can go positive and negative, still real valued, but it can be positive or negative as needed. So it comes from, comes from the magnitude, and we'll see how we do that in just a minute. And then we have to change the phase. So I use two different symbols here to indicate that they're different things. Now, don't get hung up on these particular notations. Those are just what I'm using here, and probably what Peratt used in his book. But there's no guarantee that some other author, or even me later in a note set, will continue to use these specific notations. So you have to pick it up from context. So here's the idea. Remember that a phase change of pi is the same as a sign change. So let's look at a complex plane here. There's the real and the imaginary part. So if I say, well, here's a number and here's a number, those two complex numbers. Remember, we kind of did this in the FFT note set, where we modified the twiddle factors to include a negative sign and be able to write the butterfly in a simpler form. Same kind of thing here, right? I could write this as, let's say this is 2e to the j. Oh, I'll just make it easy and assume that that's like a 45-degree angle, even though I didn't draw it. E to the j pi over 4. Well, I could write this number here is just the negative of that. So that's going to be 2e to the j. Well, it's pi away, right? So I could add pi to this or subtract. I guess I don't need the minus j there, right? It looks like I have a minus j there. Let me erase that. E to the j pi over 4. Let me subtract pi from that. So that'll give me e to the minus j 3 pi over 4. So that's that. But if I want to get back over to here, those are negatives of each other. So I could write this as minus 2e to the minus j 3 pi over 4. So that's what we're doing here. A phase change of pi is the same as a sign change. So we're going to change 2 to a negative 2. That's letting this handle the necessary sign change. And then we're going to change this by either adding or subtracting pi. So this is just an example for general complex numbers. Let's see how we do that for frequency responses. So when we do this, when we change m to an a to account for these jumps, we'll end up with a different function phi, which will be the psi with various plus or minus pi's associated with them. So kind of along the lines of what we did for unwrap, although for unwrap we didn't need to fuss or modify the magnitude because changing by 2 pi doesn't change anything, but changing by pi is going to change the sign. So here's the idea. Once we have converted into this a of omega and this phi of omega, and we'll look at an example on the next slide of how we do this. We now can write this. It looks like it's in polar form, but now a of omega need not be strictly non-negative. It just needs to be real valued. And phi of omega no longer needs to lie in minus pi to pi, because we could have adjusted that with corrections for type 2 or type 1 discontinuities. So we could also do that here. But the important thing is that this is continuous. There's no jumps, no 2 pi jumps and no pi jumps. That's the thing we're focusing on now. So let's look at an example. So that example that we had before, let's just back up and take a look at that. So there it is. So remember, this is staying strictly non-negative, so we get that point going to 0, and there's our discontinuity. So what we're going to do, I can't remember which way I did this. Let me just go. Okay, so I made the, because there's a couple different ways that I could do this. I'm going to change the sign on this part and make it go negative. So that means that I'm going to have to add or subtract pi there. It makes sense to add pi because that will take this thing up to there, right? And gets rid of that discontinuity. I could just as easily have kept this up and made this go negative, in which case this would jump down like that. So 2 options, just depends on what you want to do. So that's what I did over here. I did the first option of that over here. So here now is the a of omega is minus m of omega over this range. And then I kept it the same. And we could reverse that like I showed on the previous slide or discussion just a minute ago. There's our amplitude function, the a of omega, rather than a magnitude function. And then we add the pi only over the region where we negated the magnitude. And we end up with something that looks like this. So notice that we get a line. And but it doesn't go through 0 at 0, which is what we should have if we are expecting odd symmetry of the phase. So warning, when we do this so-called continuous phase representation, we might not get the expected odd symmetry. We only get that odd symmetry in the magnitude phase view. So just keep that in mind. But notice that this is a line, and you may remember discussions of things called linear phase. So it looks like we might want to call this linear phase, but this is different from the standard linear phase, and we'll talk about that in a subsequent slide. But that's the idea. So we've got these two types of discontinuities. We can fix both of them. Type 1 doesn't require any fixing of the magnitude, and type 2 requires us to transition to, if we want to explicitly fix it and see what the resulting phase looks like, then we need to do, we have to abandon that old idea and switch to this new idea, something called continuous phase representation. As far as I know, there's no canned MATLAB function that will do this for you and then plot it. I could be wrong, but I'm not aware of one, but it'd be nice to actually have one. Okay, so that leads us now to revisit the concept of linear phase. So in your signals and systems class, you probably should have learned about ideal filters, and you should have learned that they have linear phase in the pass band, and that was a very specific thing. And usually it's only discussed for low pass filters, although you can do the same characterizations for high pass and band pass and so forth, all the classic pass filters. But we got there by saying a signal that resides entirely in the perfect pass band of an ideal filter. So none of those things can really happen in the real world, but we're talking concepts. So a signal whose frequency or whose spectrum lies entirely in the pass band of an ideal filter should come out looking exactly the same as what went in, except we allow a time shift or a time delay. More specifically. And then we argue that that time delay corresponds to a phase that is a line that goes through the origin on the phase plot. So that's how we get to this idea of linear phase. And here's the simplest example, just a pure delay. So the input is x and the output is x of n minus L. So that's the simplest example. And if we were to convert that into a frequency response view, here's the replacing z by e to the j omega, and we get something. If we find the angle of that, the angle of that is just minus omega L. That is a line with a slope of minus L, and it goes through 0 at omega equal to 0, so an intercept of 0. And now we can generalize this idea. So we have this concept of linear phase. I'm not going into lots of detail on that because you should have seen that already. We can generalize this and say, well, a filter that may not have this exact idea of linear phase with a slope of minus, some negative slope, and I should have stated this explicitly, and it goes through 0 at omega equal to 0. Well, now we have a generalization of that. So generalizing this, we say a linear phase is a filter that has a continuous phase representation that looks like this. And so now the slope of that is not L, it's minus tau sub p. So if you were to take this phase here, not accounting for any phase issues for that, right? That's now a function that can go positive and negative. So we look at the continuous phase representation, and if it looks like it is a line that goes through the origin, and we look at its slope, that slope is going to be called the phase delay. And the units are in samples, just like we had up here. And you can see that the units should be in samples. The thing next to the J always has to be in radians. omega is in radians per sample, so tau sub p must be in units of samples. And so that tau sub p is the phase delay. And up here, we thought about it as a integer number of sample delay, and so the slope was an integer number of samples. But in general, this tau sub p does not need to be an integer number of samples. So that's interesting, and we'll see that on and on, over and over throughout the course. So here's our definition. Linear phase, and here I'm resorting to, we're using that phi of omega as the continuous phase representation, is a line with slope of some minus tau sub p and an intercept of 0. So that's key. So if we have a filter where the pass band is, we'll just say approximately equal to 1 in the pass band, and the signal spectrum lies entirely in that pass band, then this linear phase will, with the exception of this approximation, will just impart a delay of tau sub p samples. So that's easy to interpret if tau sub p is an integer. It looks just like that, even though it can be a more complicated filter than that thing. So that's what I say here. If tau sub p is an integer, the input just gets delayed by tau sub p samples, right? Remember, inside square brackets here, n is an integer. Everything inside the square brackets has to be an integer, so we can't put tau sub p in there unless it's an integer. So, but that's for the case where tau sub p is an integer. Now, if tau sub p is not an integer, which it could be, I say that up here, not necessarily an integer, we have to think carefully about what this delay is doing. So here is how we think about it. We take the x of n and we imagine it being reconstructed to its perfect ideal x of t. Claude Shannon tells us we can do that. So whatever that reconstructed x of t is, we then imagine resampling on a new grid. That grid is shifted by tau sub p samples, non-integer in this case, and then multiplied by the sampling interval. So we are reinterpolating the original signal at a fractional delay. Well, there could be an integer part in front, so that tau sub p could be like, 3.4 samples. So that's how we do that. That's how we think about that. And this will play a key role later when we're trying to make things like flangers and choruses and things like that. Those are audio effects that we'll be talking about. So that leads us now to define something called phase delay. So we can define this for any filter. We start with the filter and we find its continuous phase representation. So I say that explicitly here. And then we convert the continuous phase representation into the phase delay. So this is the phase delay of that filter. Notice that in general, it's a function of omega. So in the previous two examples, we talked about a phase delay being constant overall frequency. That's because it was a so-called linear filter. But to find it in general, we take whatever the continuous phase representation is, divide it by the omega value. So this is a function of omega divided by the omega value, and we stick a negative out in front. And then just for units, right? This is in radians divided by radians per sample, and we get sample. So the phase delay can be something that is a function of frequency in general. But for linear phase filters as we define them, let's go back and look. How did we define it? Linear phase, we say that the phi of omega is just minus omega tau sub p. So we take minus omega tau sub p times omega. I misspoke. Or maybe I didn't misspoke. I just have it in the opposite order. Minus omega tau sub p. Yes, just the opposite order there. So minus omega tau sub p, or the other way around, divided by omega. And the omegas cancel, and the negatives gives us tau sub p. So linear phase filters have a constant phase delay. Nice. So that's a way of thinking about linear phase filters. We define the concept of phase delay, and we say, oh, all you got to do is check the phase delay, and if the phase delay is constant, it's this linear phase filter that we talked about. Let's think about putting a sinusoid into a linear phase filter. So we know that the phase looks like this, and we know how to analyze how a sinusoid goes through a linear time invariant system. Two things happen. I covered this back in my review video for this course. Although we did it for the magnitude phase, but it's obvious how it carries over. We evaluate the amplitude function at the frequency of the sinusoid, and we evaluate the phase function at the frequency of the sinusoid. And now what happens? Well, now we see that we've got an omega 0 here and an omega 0 here, so we factor that out, and that shows that the phase delay shifts the sinusoid. So again, remember that if this is not an integer, we're just reevaluating this cosine on that new grid. Here it's not an issue because we're not saying I only have samples. We have a function that we can at least conceptually think about recomputing on that new grid of points. But the important thing here is the phase delay comes in through the phase shift of the filter. And so that is one reason why it's called the phase delay. And we can also see that every frequency has the same delay, right? Doesn't matter what omega 0 is, every frequency would get delayed by the same amount. So that's kind of nice. Think about a signal being built out of a bunch of different sum sinusoids. So think Fourier. A linear phase filter is going to have a delay or a phase such that every frequency gets delayed by the same amount. So all of those Fourier components all end up at the output lined up the same way they were before. That's a nice way to think about it. Now, there is a command in MATLAB that will allow you to compute phase delay. And it's called in pretty much the same way that freq-z is called. And like I said in the review, so I-DSP-0b was one of the review videos. I said there's various ways to call freq-z, and I also told you about my philosophy. Learn one very general way to call freq-z and just stick with that. And so my way of doing it is I create a vector that's in radians per sample. Even if I ultimately want to look at this as a function of frequency in hertz, I discussed that back in this video as well. I'll do it this way first, and then I convert the W into an F and plot that. But here's the command. You put in the coefficients for the numerator coefficients and the denominator coefficients. You put in your W vector that you make in radians per sample, and it will compute the phase delay. You don't have to use P delay as the variable name, but that's a convenient one. Okay, so there's phase delay. Now let's talk about a generalized linear phase filter. So we had linear phase filter, and now and remember the continuous phase representation had a phase that had a constant slope and an intercept of 0. So now we're going to generalize this, and we can see already what we're doing. Here's our amplitude of our continuous phase representation form. So our focus isn't really there. Let's focus here. There's the phase. That's the continuous phase representation. And so I'm saying a generalized linear phase filter has this form. It's different from our linear phase without the generalized out in front. Okay. And we're going to call this tau sub g group delay. And just like before, it's got to have units of samples, same dimensional argument as before for the phase delay. So we say a generalized linear phase, this is the continuous phase, representations phase, is a line with slope tau minus tau sub g and an intercept phi sub 0 that is not equal to 0. If it were equal to 0, that would be our non-generalized linear phase. So I'm just saying this explicitly to point out that this is different from what we saw before. And we can see that this type of filter can't really be a low-pass filter or really a band stop filter. Could be band pass, could be high pass, because we need A of 0 to be equal to 0. And the reason that we need that is because if we put in a DC value into a filter where this is not true, then we're going to get a complex DC value out, and that's kind of a violation of a ground rule for the kinds of filters that we're talking about here. So let's think about what this is telling us. So remember, for the phase delay, we looked at a sinusoid where this was a constant out in front. Now we're going to imagine a sinusoid that has some changing envelope out in front. I used E of n so that we can think of E as being an envelope of the filter. If you've studied communication systems, you learned that concept. But basically, I don't have to go into much more detail here. Just I'm telling you exactly what it is. And this omega sub 0 is chosen to shift the spectrum of E of n out so that it lies in the pass band of the filter that we're considering, where the pass band amplitude is approximately equal to 1. I suppose it could be minus 1 as well, but let's just stick with 1 for the time being. So the pass band lies away from omega 0, omega equals 0. That's because of that constraint. And that's why we're imagining a signal E whose spectrum has been shifted up to be centered at omega 0. Then I don't go through the details of this, but it's pretty straightforward. You can figure it out using Fourier analysis. But again, the point of this course is not to go through all these theoretical computations. So I'm going to just make some claims sometimes, and you'll just have to believe me or go seek out places that talk about that. But if we were to analyze this, we would find out that two things happen to this. One is that this gets delayed by the tau sub g, and I'm here assuming integer delays just so I could more easily write it out. But the tau sub g does not need to be an integer. So if it's not, then I have to think about, through some complicated notational means to show that, and I chose not to do that. So this was just a assumption out of convenience for notation purposes. So the group delay impacts this envelope out in front. And look, the phase delay affects the so-called carrier. I'm using terms from communication systems. And you can look in the literature. The physicists actually kind of pioneered this thinking with group delay. And there's a reason why it's called group delay from a physics point of view, propagation of waves through media and things like that. But this is what we need to know. Two things happen. Group delay affects the envelope and phase delay affects the carrier. And that's kind of interesting. So I'm just saying that in some big yellow boxes here. The envelope or envelope is delayed by the group delay, and the carrier is delayed by the phase delay. But what is that phase delay? Notice that I'm saying it's the phase delay, not times omega 0, but evaluated at omega 0. That's because for this type of structure, this does not lead to a constant. It ends up being a function of omega. So you can take that and try it out. Make a plot of this, then make a plot of that phase being divided by omega 0 with a negative out in front. And you'll see that for a generalized linear phase, you have a constant group delay, but a frequency-dependent phase delay. So that's kind of interesting. So here's our definition of group delay. Where does that come from? Well, if we go back and we look at this, so if we were to take this function here, which is a line with a non-zero intercept and a slope of minus tau sub g, if we were to take the derivative of that, the intercept has no impact on the derivative, and we get the slope, and then we put a negative out in front to get tau sub g. So there is our definition of the group delay for any filter, not just a generalized linear phase filter. But here's the key. Both of these phase delays, phase delay and group delay, are both defined in terms of the continuous phase representation. So you need to figure that out first. Fortunately, there's a MATLAB command that does both of these for you. And again, the units, just as before, we would have, this is in radians, and so d phi is in radians and d omega is in radians per sample. So it's units of sample, just like before. So for generalized linear phase filters, the group delay is a constant, does not depend on omega, so not a changing function of omega. And then we saw that for regular linear phase filters, phase delay is a constant. So those are the two big ideas to keep in your mind. Now, here's a filter with a transfer function that looks like that, and we can plug the B coefficients and the A coefficients into the command group delay. And like I show back in this video, make a W vector in radians per sample. Okay, really I should think of that as an omega vector, but can't really, I don't like to write out omega as a variable, just kind of long and clumsy. So I just use W. So that is my discrete time frequency in radians per sample. I put it in and I run the group delay command, and it will compute the group delay for me. And then I can plot it versus omega, or more often than not, we want to plot it versus a frequency in hertz. So we would convert that omega into hertz, remembering that pi converts to fs over 2. Then we can make plots, and then you look to see, is it constant or what is it doing over frequency? So let's look at a so-called narrowband signal, similar to what we just saw, and in our example for group delay. For a general RC-SR filter, doesn't necessarily have to be linear phase or generalized linear phase, just whatever it is. So it has its amplitude form and its continuous phase form. If we put in this envelope with carrier, just like we talked about before, and we choose it such that this E is its spectrum moved up to be centered at omega 0, will lie nicely inside the region where the magnitude, or amplitude rather, amplitude response is approximately constant. And if this is such that this thing is constant, Then, so now we're talking about the generalized linear phase filter. The output can be approximated, and I'm assuming integer delay for the group, but I'm just doing that so that I don't have to fuss about notation for interpolated versions of this. We get something that looks like this. We get the tau sub g evaluated at omega 0 and tau sub p evaluated at omega 0. I misspoke. I'm not saying that that this thing is a constant. I'm just saying we're going to evaluate this at that function or at that frequency. Then that shows up here and that shows up here. If we were to use a different omega 0, we would get a different group delay. So sorry about that. And our relevance to audio, well, we can think about a musical note as a sum of harmonics, right? That comes right out of Fourier. But there's an envelope embedded on that, right? When you play a musical note, you play a single note on a piano, the amplitude or the volume starts very rapidly and then dies down almost exponentially. But now imagine playing a violin, but you play it in such a way that you start very soft and get louder and then softer. So this is something that we can use to emulate or mimic the growing amplitude or volume and decaying volume and maybe sustained volume in between there of a note, right? And then this sets the harmonics of those. And since a string vibrates kind of harmonically, we can add in a bunch of different harmonics, and we're only adding up to some K. So that's a pretty good model for a single musical note played on some instrument. And now let's think about this. We can use our result up here where we evaluate the group delay and the phase delay at all the different frequencies that are going on in this note that we're playing. And then here's the clincher. If we say, let's make sure that this filter is a generalized linear filter that has a constant group delay, then every one of these harmonics will end up with the envelope delayed properly. And so all the envelopes will line up with each other. If that's not true, then we'll get harmonics whose individual envelopes will now no longer be aligned, and it might sound not right. You'll have certain harmonics starting a little bit earlier and other harmonics starting a little bit later, and that might not sound good. I'm not saying it's wrong to do it. I'm just saying it's not necessarily retaining the fidelity and the nature of the note. So if you want to retain the nature of that note, you'd like the group delay to be constant. And you can see I've switched back to continuous time here. All the ideas are the same. And so that's the idea. So throughout the course, we'll make reference to phase delay and group delay, although group delay, because of this thing, will be something that we'll usually focus on more than phase delay. Okay. I'll hopefully see you in the next set of notes.